So he'll be talking about Caliper, a precise and responsive traffic generator, which is based on NetFPGAs. Yashar, take it away.
Thank you so much for the introduction. I'm going to talk about Caliper, a precise and responsive traffic generator today. This is a joint work with Mani Agobadi, Jeff Salmon. These are two of my graduate students. And Greg Stephan, another faculty member in the Electrical and Computer Engineering department, and Martin Lebrec, who is a former student of Greg. Making any changes to the network is extremely challenging. If you want to change any network components or protocols, you need to extensively and accurately experiment with the proposed change in real or realistic scenarios. Real network experiments are extremely difficult, mostly because network operators are risk-averse and they don't like changing their networks, rightly so because of the intrinsic risks that are associated with changing any complex system like a network. And therefore, before allowing any change in their network, they require you to do a lot of testing, exhaustively test all the possible scenarios to make sure things can't go wrong. What this means is that since you can't do real network experiments, the only remaining option is testbed experiments. A major question here is how can we generate real or realistic traffic if we want to do testbed experiments? And we need the traffic to be as close as possible to real traffic in order to make sure that the results we get from the experiments are applicable in practice. And if we want to do this, if we want to generate traffic which is real or realistic, there are three main challenges. The first one is modeling. Basically, we want to make sure that we understand what the real traffic looks like, what are the parameters that we need to sweep, what are the appropriate sets of combinations of these parameters that we need to have. And this problem has been studied extensively in the literature, so I'm not going to talk about that today. Once you have an accurate model of the real traffic and you want to basically do a network experiment, you need to turn that model into real packet injections to your system. So the second challenge is how can we accurately inject packets in the appropriate times to the network. And the third challenge is how can we ensure that the generated traffic is responsive to network state. Basically, there are things that can happen in the network that affects the future of packet arrivals to the network, and it's very interesting and challenging to ensure that the traffic can respond to those events in the network. So these two are the challenges that I'm going to focus on in this paper. Let me give you an example before continuing. Let's imagine we want to do some experiments with router buffer sizing. And for the sake of argument, let's assume we want to reduce the buffer sizes to a handful of packets, 10, 20, up to 50 packets. This is what I did for my PhD thesis, and there are extremely difficult challenges with performing such experiments. First of all, if you want to do real network experiments, no operator would do this for you. No operator is willing to reduce the buffer sizes from tens of millions of packets to just 10, 20 packets in an operational network. And if you want to do testbed experiments, you need to generate traffic which is extremely accurate. Accurate in the sense that packet injection times have extremely critical role in the results you get. Even if you delay a packet by a few nanoseconds, it changes the shape of the traffic, the burstiness of the traffic, and the drops you're going to see in your network. And as a result, the experiment results would change depending on how you inject packets to their system. And assuming even if you assume you can create very accurate packet injections, we cannot ignore the TCP feedback loop. Once you drop a packet, that dropped packet is going to have an impact on the future of packet arrivals. So if you have a traffic generator, you need to make sure that you take that into account. Other examples of scenarios where you need these properties is when you're testing any new congestion control scheme, let's say DC-TCP, the new proposed congestion control scheme for data centers, or denial of service attacks which rely on very small rate and timing accuracy to create the attack. So what's the problem with existing solutions? the simplest way to generate traffic is basically take a recorded log of packets, a PCAP file, and replay that. One example, a system that uses this approach is Stanford's packet generator, SPG, which is extremely accurate in terms of injection times. But the problem here is that we are losing the feedback loop. Since you're replaying a recorded sequence of packets, if some event happens in your network which impacts the future, you're not going to capture. And as a result, you cannot adapt the traffic generation to based on higher level models. In this figure, T1, T2, T3 are events in the past. Something happens in the present, and it changes all the future events. And a system like this is not able to capture that. The second class of solutions, existing solutions, are commercial traffic generators. The problem with these, at least from an academic's perspective, the first one is they're very expensive. They cost hundreds of thousands of dollars, and they're very inflexible because of their proprietary nature. As an academic, I would like to change and play with these things, and modification of these devices is extremely difficult. The second problem here is that you don't have full control on all the internals. In this figure, you would like to generate traffic as if it comes from, let's say, thousands of nodes. The traffic generator is going to mix the packets from different flows in a specific way, and you have no control on how to change the ordering on the underlying topology. There are a lot of parameters you cannot control. And the last problem here is that you have limited precision. These traffic generators are usually created for macro level experiments. You have a server farm. You want to see if you inject 1 million flows, what happens to your server farm? Can the servers handle that much traffic? But in terms of precise injection of packets, precisely emulating, let's say, protocols like TCP, they are not very accurate. As a result, they're not very suitable for time-sensitive experiments. And the third solution that exists today is using a software-based traffic generator along with a commodity hardware, commodity network interface card. And basically, you generate packets in software and you inject them through the NIC card to the network. The problem here is that the accuracy of the system is bounded by timer resolutions, which is for some applications is not good enough. And the second major problem, I would say, is that you might have unpredictable behavior depending on parameters which are sometimes hidden to you and depending on the actual hardware you're using. One example I can give you is in our buffer sizing experiments, we had 2 racks of machines which looked identical, and we were doing some experiments and the results were completely different. And after spending some time, we realized in one of the 2 racks we have machines which have Intel NIC cards, and the other set had Broadcom interface cards. And by default, they have the interrupt coalescing option was on in one of them. The other one, they had the parameter off. So these differences can lead to significantly different results in time-sensitive experiments. Even if you use the same hardware, depending on the driver you have on top of that hardware, you can have different results. In this figure, we are using an Intel NIC with 3 different drivers, and the x-axis is packet interrival times. And as you can see, there is considerable differences in packet interrival times depending on which driver you're using here. So what's the solution? We have created and built this tool called Caliper, which is a precise and responsive traffic generator based on the NetFPGA platform. Caliper has very accurate packet injection times, and you explicitly tell Caliper when you want the packet to be injected to the network, and it tries to stay faithful to that time as much as it can. The packet injection times can change dynamically based on the feedback you get from the network. So if a packet is dropped in your network and the acknowledgement is delayed, or if something causes congestion in your network, the future injection of packets can be a function of that state. And it is easily integratable with existing software-based traffic solutions. Basically, you can have a simple tool like iPerf, or a complex simulation environment like NS2, you get packet inter-arrival times from that system, and Caliper can inject packets to the network accurately based on that. So here we have the high-level schematic of Caliper. As I mentioned, it's built on NetFPGAs, and we have built a platform for developing packet processing applications, which we call NetThreads. What this means is this is a platform where you can write your code in C, and it translates it to something that can run on NetFPGA, which might not seem significant for people who have background in hardware. For me, because my students are in computer science, it reduces the development time from months to a few days. They can easily add or remove functionalities to this thing. So we have three major components. On the left-hand side, we have a software, which can be a user space process or a kernel module, which generates packets. Those packets are fed to a NF2 Linux driver, which in turn communicates through PCI with the NetThreads applications and injects packets to the network. So let me go through these steps one by one. The first step is packet creation. For that, we need to have accurate definition of inter-transmission times and payload sizes of packets, which can come from a fixed, which can be fixed or can come from a file, or we can have an application that generates those inter-transmission times and payloads. And in the case of an application, as I mentioned, it can be a user space process or a kernel module that creates a sequence of packets. And once packets are generated, a description of that packet along with the exact injection times are sent to the driver. And the communication with the driver happens through a netlink socket, which means we can easily replace this by any other user process, user space, or kernel code. The NF2 Linux driver is based on the original NF2 driver from Stanford University. And what it does is basically receives these descriptions from the netlink socket and builds a command packet which contains multiple of these packet descriptions, and sends this command packet to the NetThreads via the PCI bus. And I emphasize this is PCI, this is not PCI Express, so it can be a bottleneck if you're generating high volumes of traffic and you're sending all the packets through PCI. It can be a problem. You cannot copy all packets across the PCI bus in this case. And the idea we had was just to simply remove the payloads of packets. You can ask NetFPGA to add payloads as zeros, or any predefined payload pattern that has been already uploaded to NetFPGA can be added to a specific packet. And to minimize PCI transaction overheads, this driver gathers multiple of these packet descriptions, as I mentioned, into a single command, and that single command is transferred to the NetThreads application, which is sitting on the NetFPGA. Here we have 8 threads executions in NetThreads, and 7 threads here receive packets from the driver, and prepare packets would be transmitted on the output memory. And one process here, one thread sends packets from the output memory to the output line at exact times. One advantage of Caliper is that it can be easily integrated with existing tools. From the perspective of the kernel, this is just a network interface device, and as a result you can easily integrate with any existing solution that talks to a network card. Packet transmission times come from some application. As I said, it can be as simple as ping, iperf, or a complex simulation environment like NS2, and packets are received from that application, injected to the network, and packets that come back to from the network are again delivered to the application. And here there is some challenges in synchronization, especially if you're running a simulation application. The packets that come from the network, they have an impact on your simulation or emulation environment, which means you need to run the simulation, because there is difference between the real time and the simulation time. You need to run the simulations and slow it down whenever you can to make sure that these two times stay synchronized and you don't see packets in the future basically in the system. So we have done this. We have built an NS2 integration. You simply define a topology like you would in NS2 and creates a sequence of packets. These packets are fed to Caliper, which injects them to the network. And whenever a packet comes back from the network, Caliper takes that and translates that to the packet format that NS2 real understands and feeds it back to NS2. So this way you can create a complex simulation environment which generates real packets using Caliper. And in fact, in a later project, what we have done, we have made it parallel. So you can have multiple instances of NS2 running on different machines, talking to each other and generating a stream of packets. But I'm not going to talk about that here. So to evaluate, the focus of evaluation is flexibility and accuracy. I'll talk mostly about accuracy here. So we have 3 boxes, a sender which generates the traffic. We send the traffic through a NetFPGA router. And the reason we do that is in order to measure packet interarrival times, we need something which is extremely accurate. And we use NetFPGA for that purpose. There is a variation of NetFPGA router which can log packet arrival times very accurately, and we use that to measure how closely we can mimic the desired inter-arrival times. So in this figure, what we have is we have a Caliper sender which injects packets at a fixed rate to the network, and the x-axis in this graph is different rates in megabits per second, and the y-axis shows the error from the desired rate, basically 95 percentile of the absolute error here. And we have 3 different experiments here. The black bars show Caliper, the white bars show Stanford's packet generator, and the gray one shows a commodity NIC. And you can see that Caliper and Stanford packet generator, they have almost 3 orders of magnitude less error in injection times. So they are extremely accurate. The only interesting remaining point here is that when you saturate the link, the error goes down even with a commodity NIC. This is because you're sending packets back to back, so there is no error. There is no variation in packet interarrival times. In the next experiment, we change, rather than sending packets at fixed intervals, we use a Pareto interarrival distribution. It doesn't need to be Pareto. It can be any distribution you want. And as you can see in this graph, the x-axis is interarrival times, and the y-axis is the CDF, basically. And you can see that the input and output, what you desire and what you get from Caliper, match very closely. In the next experiment, what we have here is interarrival times, again, as the x-axis, y is the CDF, but for a case where we have variable packet lengths. So far, all the packets were of the same size. And again, you can see that the input and output to Caliper match very closely. The last experiment in this group of experiments is basically when we use TCP instead of UDP. And this is interesting because the Stanford packet generator doesn't work here. It fails because it's replaying a pre-recorded set of packets. So if something changes in your network, you have a packet loss. If acknowledgements are delayed, it cannot react to those. So we don't have those bars in this graph anymore. And we are comparing Caliper with the commodity NIC. And as you can see, we still have almost 3 orders of magnitude reduction in error using Caliper. And finally, the last experiment we have done here is to compare Caliper with a software-based emulator. For this specific experiment, we are using NISNet, and the objective is to add fixed delay to packets. Basically, we generate packets using Caliper, as you can see on the left. We inject packets to those networks. We measure interarrival times. Then we use a software emulator to add 100 milliseconds of delay to every single packet. What that means, ideally, is that packets are going to be delayed, but the interarrival times are not supposed to change. And then we measure after injecting packets to the network again. And in this graph, you can see the observed interarrival times. The ideal interarrival time is 70 microseconds, which, as you can see, the dashed line is what Caliper injects packets is exactly 70 microseconds for all the packets. And if you look at the packet interarrival times after passing through NISnet, you can see that 40% of packets have a very small interarrival time. The interarrival time here is actually the length of the packet. And for 60% of packets, you see something between 110, 120 microseconds. Ideally, these two graphs should have matched, which shows software emulators have intrinsic problems because of the timer resolution issues. So let me summarize. Generating realistic traffic is essential, but it's a very challenging problem. We propose a simple tool called Caliper, which dynamically and accurately tries to generate traffic. And it can be integrated with existing software traffic generation tools. And the timings are extremely accurate because you're using hardware level timers. And with that, thank you very much for your attention, and I'm happy to answer questions.
Thank you, Yashar.
Absolutely.
Okay, are there any questions?